the first thing I wanted to talk about was sort of introduction and why we want to build sPHENIX, what we want to study with it. And so the idea behind all heavy ion physics really is to study QCD, right? So it's the strong force is governed by QCD. It experiences these attributes called color confinement. So at the low energies and large distances, the QCD coupling is very large. And all of your quarks and gluons are only really found in color neutral bound states, like the proton or the neutron. On the other side of things, at very high energies or short distances, the QCD coupling becomes very weak. And so you have this phenomenon called asymptotic freedom, which means that at the long distances, the quarks and gluons just sort of act like free particles. And so these effects kind of come together into the QCD phase diagram. So here you can see as a function of temperature on the y-axis and the baryon chemical potential on the x-axis, different phases of QCD, and the phase in which particularly interested is quark-gluon plasma that's up here at this sort of high temperature range. And so there's a lot of interesting things that you can do from the LHC and also RHIC experiments. And since I'm showing the phase diagram to a bunch of people who work on STAR, I have to point out that STAR has done a lot of work on the beam energy scan, which looks for this critical point in the phase transition between the sort of normal hadrons and the QGP. So the QGP is this hot, dense state of matter where the quarks and gluons become deconfined because of this asymptotic freedom. And we believe that the universe, basically a microsecond after the Big Bang, it was formed of a QGP. And so there was QGP, and then it expands, cools, and you eventually form hadrons, and then nuclei, atoms, all the way up to today. So obviously we cannot go all the way back to the beginning of the universe to study the QGP. So where we can go instead is to recreate those conditions in the lab. So there's two facilities where you can do these types of experiments: the Large Hadron Collider at CERN and Relativistic Heavy Ion Collider at Brookhaven National Lab on Long Island, which is where I work. And so currently there are two experiments at RHIC. There's the STAR experiment and then sPHENIX, which says assembly underway because this is an old picture, but actually the data taking is underway. So that's what we're talking about today. And I'm going to focus a little bit on jets in heavy ion collisions because that's kind of my area of research. So I wanted to sort of point out QGP in general first. So in the lab, right, you produce them in heavy ion collisions. You produce the QGP, which then expands, cools, just like the early universe, turns into hadrons, and that's what hits your detector. So the question is, how do I take this that hit my detector and figure out things that happen here? So the first thing you could do is just characterize what the QGP looks like. And so if you're looking at heavy ion collision here, you can see that, okay, we have two nuclei that have hit each other, forms this sort of oval overlap shape, which then expands. And because of the pressure gradient in here, it expands in a certain pattern, which we can then measure in our detectors. And if we compare that to models with a sort of hydrodynamic description of that, we find that the quark-gluon plasma exhibits this sort of hydrodynamic behavior with very low viscosity. So a lot of times people will say, oh, the QGP is a nearly perfect fluid. This is what they're referring to, this viscosity or density being very small. So we know that the QGP behaves like a liquid. And then the next question is why? And so if you wanted to figure out why water behaves like a liquid, you would go and look at the details of what the water molecules are doing. And so we want to do the exact same thing with the QGP. We want to put it under a microscope and understand the small scale structure. And so you might think, okay, well, obviously we can't just throw it under a microscope. But what is a microscope really doing? Well, it's shining some light in, it's shining a probe, and it's measuring what you can see. And so we want to do the same thing with the QGP. We want to send in a probe, we want to measure what comes out. Unfortunately, the QGP is very short-lived, and so that's not really feasible. But we're really lucky in that the QGP is formed in these collisions that also form its own probe. And that probe is jets. So if you have a high energy scattering in the same collision that produced the QGP, then you can produce high energy outgoing quarks-gluons. And these are going to go through the QGP and interact because they have a color charge. And they can lose energy as they interact with the QGP. And so you're actually probing what the quark-gluon is doing. And then these outgoing quarks and gluons, as I said at the beginning, right, you can't see it in nature by itself. They're going to fragment and turn into a spray of particles, which we can cluster together. And that's what we call a jet, and that's what we measure in the detector. I wanted to highlight here that jet measurements in systems without QGP are also extremely important for understanding the effects of QGP because it provides the reference for what is the jet production looking like in the absence of the medium. And jets are our probe because if you look at them in the vacuum in this reference system, the production is extremely well modeled by derivative QCD because of the energy scales involved. And so here's a plot of the just jet cross section measured in Atlas in proton-proton collisions, and you can see that the calculations agree very well with the measurements. In the medium then, you have, okay, this is a silly cartoon that I made, but right, you have your proton-proton collision here, your spectrum. And then if you lose energy, this is going to shift over to the lower PT range. And so you're going to end up with a sort of depletion in your jet spectrum. And what this looks like in real data is something like what's on the right here, where the lines are for proton-proton collisions, and the points are from lead-lead collisions. And so you can see that there's a depletion in the number of jets that you see at a given PT. And these are scaled by this factor, which essentially scales up the proton-proton collisions to the amount of collisions that you're actually getting in a lead-lead collision, because there are more protons. So then if you want to sort of quantify, okay, how much energy was lost, how much has this spectrum really changed, you can take a ratio. And so here, this is looking at this observable we call the RIA. This is the ratio of basically just what you measure versus what you would expect. If there was no QGP, no effect, it would be 1. You can see here that it's very much less than 1 for these very head-on collisions. And as you go to more glancing collisions, it comes closer and closer to 1. There's less QGP produced. The jets are interacting less, and they're losing less energy. So the RAA is a great way to show that, okay, jets lose energy, the spectrum is magnified, but then the next question is, okay, well, what else? What else is really affecting this energy loss? And there's a number of different things that you can look at to understand the energy loss more differentially. The first thing you might think is, okay, a jet will lose more energy if it sees more QGP. So this jet, a lot of the QGP is probably going to lose more energy than this one that goes out only and sees a little bit of it. And so you could measure something like the path length dependence. You could also look at what the jet actually is. So is the jet coming from a gluon? Is it coming from a light quark? Is it coming from a heavy quark? So we expect that heavy quarks are going to interact less with the QGP, lose less energy. And for quarks versus gluons, you know that the gluon actually fragments into a broader jet, and so that could potentially have some effect as to how it's interacting with the QGP. If the QGP is seeing it as less of a single composite object or more of a spread out multiple part object. And so along that vein, you could also look, instead of picking out a specific flavor of your jet, you can look directly at what is the structure of the jet and how is that structure, how does the structure influence the energy loss? How is the jet modified? And so you could look at something like, is this jet that has 2 prongs really seen by the QGP as a single prong object or as a 2-prong object? And so those are some of the questions that we're really trying to answer with sPHENIX. And so I like this picture a lot. This is a picture of the installation of the inner E shell of sPHENIX. So they basically built the entire thing and just slid it into the magnet. I thought that was pretty cool. So this is the sPHENIX physics program sort of overview. I'm very biased, and so I'm going to mostly talk about jets. And so, jet structure, understanding the energy loss of jets, also looking at different flavors of jets, heavy flavor, that type of stuff. sPHENIX also has a lot of interest in doing Berkowitz spectroscopy, so looking at the epsilon states specifically. And then finally, sPHENIX has a cold QCD program, which I'm not going to talk about, but is also one of the major driving points for the proton-proton learning that we discussed with polarized protons. So sPHENIX is a very new detector that was built at RHIC and took first data last year. So it was basically built, and then a few weeks later we were taking data. So it's very, very new. It has a full calorimetry system. So this is really towards the jet physics, because we wanted to be able to unbiased hadronic and electromagnetic components of calorimetric jet energy. So it has an EM cal, which is the big made of tungsten blocks with scintillating fibers inside of them. And then it has a two-part hadronic calorimeter, so one that sits inside the magnet and one that sits outside of the magnet. And these are scintillating plates and metal plates, sort of sandwich. I mostly work on the H-cal, so if you have any questions about the H-cal, I'm happy to answer them. The other systems are the precision tracking system. So here we have 4 parts to the tracking system. There's the MBTX. This is a silicon-based vertex detector. And so this is really key for doing the heavy flavor physics in sPHENIX, because you can tag heavy flavor decays from the vertex detector. The INTT is another silicon detector, and it sits outside of the MBTX, and this has really fine timing resolution, which is important for the tracking in terms of like rejecting pileup. Then there's the TPC. So this is the time projection chamber. It's sort of the largest part of the tracking system, and this is what provides the momentum measurement of the tracks that are bending in the magnetic field. And then finally, there's this outer layer, which is called the teapot. It's the TPC outer tracker, and it provides basically just like an extra point on the outside for calibration purposes for the TPC. I don't have a bullet point for it, but there's also a number of sort of event characterization detectors in sPHENIX. So there's an event plane detector. If people are familiar with the STAR event plane detector, it is almost identical to the STAR event plane detector, but we added an S for sPHENIX. And then we have a minimum bias detector. This is used as the triggering system for heavy ion collisions and also the centrality determination. And there's a 0-degree calorimeter that's way out there on either side. And then the last thing that you need to be able to do these measurements of IPT rare probes in these collisions is a large data set, because these are rare processes. And so the key to getting a large data set is to have fast readout and be able to take a lot of data. And so sPHENIX is designed to take 15 kilohertz of triggered data, which is from the calorimeter systems. And then the tracking detectors also have a capability of being streamed. So you can just continuously take data from the tracking detectors. And so this allows for additional statistics, especially for like low PT heavy flavor type probes that you couldn't necessarily trigger on. So this is the nominal sPHENIX 3-year run plan. So we were built basically just to run for 3 years. In 2023, the plan was to do commissioning and a little bit of physics data in gold-gold collisions. 2024, this past run, the plan was to take the proton-proton reference data, as well as the polarized protons and proton gold for cold QCD measurements. And then finally, in 2025, the plan is for this very large statistics gold-gold data set, which is really the key data set for that physics program. So anyone who's worked in experimental physics knows that things do not often go to plan. And so this is the reality of what happened in sPHENIX in run 23. So this was our plan, right? Commission the trigger system, the calorimeter systems, the data acquisition, commission the tracking systems, and collect first physics data. We did really good on the first part. We commissioned the trigger and the calorimeter systems and the data acquisition pretty completely in the run and quite early on. So here is just a plot looking at the correlation between the charge in the NBD, the minimum bias detector, which is used as the trigger, and the outer H cal. We have plots like this for all of our calorimeter systems. So they're all nicely correlated. You might think it's obvious, but the way that sPHENIX reads out its data is system by system. So actually putting together the events is a little bit of a challenge. So it's great to see that, we were able to do that quite quickly. This is another pretty early commissioning plot. It's the diphoton mass distribution. So here you can see the nice pi0 peak. We have much nicer versions of these now, which include both the pi0 and also the eta. But this was quite early on. And we can even go towards more advanced physics objects like jet reconstruction, where here you can see an event display of a back-to-back diode event. The tracking system commissioning was a different story. So we were well on our way to getting things running. And then RHIC had an incident where a cryo valve box essentially blew up. And so that kind of stopped the run quite early. It was 8 weeks early. And we were not able to finish commissioning the tracking systems. And so with that, the sort of idea of collecting physics data for gold hole was pretty much out of the question. But actually it turns out that the commissioning data from the calorimeter wasn't so bad. And so we were able to do a number of measurements for sort of standard candle type measurements with the calorimeters to really show that we understand how our calorimeter systems work and we can agree with data from previous measurements. So here is the V2, the flow of the neutral pions, in blue from sPHENIX and in red from the previous pHENIX results. So you can see that these agree pretty well. Again, this is commissioning data. It really wasn't meant to be physics data, so the uncertainties are a little large because we didn't have a huge amount of data. We also looked at the transverse energy as a function of eta in the calorimetric systems. And so here in the blue points is the sPHENIX result, and then in green is the star result, and gray is the pHENIX result. So these agree qualitatively pretty well. We know that there's some problem in our centrality determination in this data set. So this is still very preliminary, so don't get too concerned if they don't totally agree. But it was really great to see that we could actually, get physics results out of this data set that was not planned to do so. So that brings me to run 2024. And so our plans again had changed because the plans for 2023 did not get finished. And so the first thing on the list was commissioning the tracking detectors, which hadn't been finished in the previous run. So this got done eventually. And so here you can see an event display that has the tracks in the red points are from the silicon, and then the sort of tracks going out are in the TPC. So you can see them curving in the magnetic field. But I know people here probably, at least some of you are familiar with the RHIC run, and so you will not be surprised that this was not without challenges. The TPC commissioning hit some snags and was really ongoing until August. So this was most of the way through the run at that point, which means that we have a significant amount of data that is the calorimeters only, or the calorimeters plus the silicon tracking system. And so we actually took advantage of the fact that the TPC wasn't really working very well to really maximize these data sets. And you'll see in a minute that we got above and beyond our goal for calorimeter data. And so in the end, the saving grace was the isobutane, which got added to the TPC gas mixture. And to celebrate, we had a isobutane sPHENIX themed cake at our end of run. So that tells you how important the isobutane was to us. So the next goal from 2024 was to commission the calorimeter trigger system. So in the gold gold running, we had just used the minimum bias detector for triggering. But in proton-proton, we wanted to sample the full luminosity and be able to collect jets and photons. And so we have a trigger system that is based on patches, energy and patches of the calorimeter. This is again from commissioning, so the statistics aren't very good, but you can see the sort of turn-ons from the various jet triggers here based on these patches in the EM-cal plus H-cal. And so we have triggered events from 6, 8, 10, and also 12 GeV jets. And then similar triggers also for photons, and that also works for electrons. It's just on the EM-cal. So going through the actual data set that we collected. So as I mentioned at the beginning, we really took advantage of this time without the TPC to take a lot of calorimeter data. And so in yellow here, I'm showing the calorimeter data that we took. This is how much we sampled over time. And then you can see that there's a bit of change of slope here. This is when the TPC turned on and changed the crossing angle. So we had a slightly different luminosity that we were sampling there. But you can see that we really collected a lot of calorimeter data. This lot is from like a couple weeks before the end of the runs. Numbers aren't quite final, but I have the final numbers on a slide in a minute. And so this is the data set that can be used for any sort of calorimeter jet, photon, that type of study. We can use this data set. The next data set is the data set that requires both the calorimeters and the tracking systems. And so here we started a little late because of the issues with the commission, the TPC. But you can see here that we took a good amount of data within the last section of the run. Note that the axes are different here, so don't compare the lines to each other. And so this is the sample that you would use for something like jet substructure, or also the upsilon measurements, which are coming from the electrons. And then finally, because the tracking systems have this ability to take data in streaming mode, you were actually able to play catch up a little bit with the tracking systems by just streaming a lot of the data. And so the streaming data, it doesn't include the calorimeter information, but if you just need tracking information, we actually got a good amount of that coming from the streaming. And so this is really key for like open heavy flavor measurements. I forgot to point out on this slide, so this is an event display that includes tracks in the TPC going out into the EM-cal, since this is the photon conversion event. And then again, here is the tracking systems. So I would say this was a mixed success, which is why the check mark is yellow. We got over 200% of our goal for calorimeter data. It's great. Only about 30% of the goal for the full detector, and 65% of the goal for the tracking data. And so we're able to do most of the sPHENIX physics program with this amount of data. And the last thing that was really a goal for 2024 was to finish the commissioning in gold and be ready for 2025 next year. So here I have a similar plot to the one I showed before. You'll notice that the slope is all over the place. And this is because the focus was really on commissioning. It was on understanding backgrounds in the detectors and understanding performance. And so we had a bunch of interesting little changes in the beam conditions and stuff like that to really track down some of these backgrounds and stuff like that. So it's not really physics data in that sense, although I would not be surprised if you see some physics coming out potentially from the calorimeter side of this data set, since the calorimeters were mostly commissioned by the time we were. So run 2024 results. I don't have any to show you on the physics level, but if you come to Quark Matter, we will definitely have results. So I'll just say stay tuned. the run went very well for us. We were really focused on the run. And now the run is over. We're really focused on getting analysis of these results to show the quark matter, and also analyzing the gold data that we just took to be really ready for next year's run. So I've gone through 2023, 2024. What about 2025? And so here I want to show some projections for the physics that we plan to do with the big gold data set that we take in 2025, and also in combination with the 2024 data that we took this year. So in terms of jet physics, this is a projection based on the sort of nominal plan. So some of these numbers maybe changed a little bit. In fact, the calorimeter data that we took is actually higher in PB than what we have in these projections. But what we expect to be able to do is measure jets out to fairly high PT, somewhere around 70 GeV. And that gives us a good overlap with measurements that are done at the LHC. Where the LHC measurements can't really go is down to very low PT because of the large backgrounds. And so that's where sPHENIX can really contribute down to very low PT at these big energies and provide comparison both in the same region as the LHC and down to lower energies. We also expect to have large statistics for photons. I mentioned that we had the photon trigger in the last run. Charged hadrons as well. This is something that requires the tracking system, so maybe not as much as is shown in here as what we have for the PD data. But we have a good amount of that as well for things like fragmentation functions, substructure, stuff. So I wanted to bring back this slide that I showed at the beginning of sort of different things that you could study and how they affect jet energy loss. And so things like the path length dependence of energy loss, mass dependence, looking at light versus heavy flavor jets, looking at quark versus gluon jets, and then looking at jet substructure. So as I mentioned, these are all things that sPHENIX really wants to be able to address in the measurements that we do. So I have to show the jet V2 because this was my PhD analysis. And so one of the ways that you can get at the path length dependence of energy loss is by looking at the azimuthal variation of your jet yields. So you can expect that a jet that comes out this way from the QGP is probably going to see less QGP on average than coming out this way. And so that really directly tells you about the path length dependence. And so if people are familiar with like V2 in certain measurements, a lot of times people say that this is flow. For jets, it's not really flow. It's really this energy loss that's correlated with that initial geometry. And so it's really directly measuring this path length dependence. And so you can see here at the LHC, there's a lot of measurements, both in jets and in high PT hadrons that go out, high PT. Yeah, the red points were my points. And so where sPHENIX can come along and inform this a little better is at the low PT region. And so this is especially important because if you go to very low PT jets, you're getting closer and closer to the scale of essentially the QGP medium itself. You expect maybe more of an effect, more tension. Another interesting topic that you can look at is the sort of jet size dependence. So if you look at a very narrow jet, how does this lose energy different to a jet that's very wide? And so there's sort of an interplay here that it's not quite clear which effect will win out. So if you go to a wider jet, you might recover more of this out of cone energy loss, which includes more of the sort of medium response. The jet is dragging stuff along with it. But at the same time, we expect that jets with wider splittings are going to lose more energy. In fact, we've seen measurements of this. And so the question is, if you just go to a wider jet, are you seeing more suppression or less suppression? And so if you look at the LHC, this is the ratio of a large R jet to a small R jet. And you see there's kind of different answers from different experiments. And in sPHENIX, we expect to really be able to do this in the region where we have this tension at the low PT. I also wanted to point out that this one is something that can be done with just the calorimeter data. So I mentioned we have more than 200% of our goal. And so from the PP side of things, we actually will have better statistics than what's shown in the projection here. Going on to then looking at the flavor dependence. One really interesting thing that you can do in a jet system is instead of looking at jets that are produced inclusively or back to back with another jet, you can look at a jet that's produced back to back with a photon. The photon is great because it doesn't interact with the medium, and so it provides an unquenched tag of the jet probe. And so if you wanted to just compare in TP, you expect them to be quite balanced, and if you go to AA, they're probably going to be less balanced. And so this is something that we'll be able to measure, again, in sPHENIX using the calorimeter only data set. But another interesting thing that you can do is then just take these jets and look at what those jets look like. Because we know that in this production system, we expect that these jets are more likely to be coming from quark jets. And so you can actually change the flavor composition. It's not quite as much as you do in these types of systems at the LHC because of the flavor composition in inclusive jets, but you can still change it somewhat by looking at these quark jets. And so, yeah, this type of measurement with just the photon jet balance is something you can do in a calorimeter only data set. You wanted to look at something like the substructure of a photon tagged jet. That's something we really look tracking information. And so this is somewhere where maybe we're hurting a little bit in sPHENIX because of the smaller data set that we got with the full detector. And so speaking of sort of jet substructure, in photon jet systems, you can just look at it also in inclusive jet systems. And so you can look basically and try to ask, like, what is the resolving power of the QGP? Is the QGP seeing, a two-pronged structure here, or is it seeing it as a single object? How is the shape of what the jet fragments into, how is that affecting the energy loss? And so you can look at something like the ZG. This is basically related to the splitting here, and understand the jet scale. This is another measurement that is lacking a bit compared to the projections that we've shown before due to the lack of the smaller calo plus tracking PP data set that we have right now. And then the last thing that I mentioned that we wanted to look at was the mass dependence of energy loss. And so here I'm showing the RAA projection for B jets. So these are jets coming from the B quark. As I mentioned at the beginning of the talk, we talked about sPHENIX. We have this silicon vertex tracker. And so this can actually be used to tag directly the heavy flavor decay. And so you can tag directly the V jets. This one is, again, something that really requires the calorimeters plus tracking. And is something that is really statistics hungry. It's a rare process to form a B jet. And so this is something where having more PP data would be nice. So that brings me to the question of, if sPHENIX doesn't end in 2025 or run 2025, what would we want to do next? And so I think the first answer is that we would probably like to have more PP data now that the full detector is working. But there's also a lot of interest in small systems in sPHENIX. And so there's a lot of open questions about, is the QGP formed in small systems? There seems to be evidence from like the bulk side that we see flow in these small systems. But if you look at jet measurements, you don't really see jet suppression. And so there's these questions. And sPHENIX could do measurements like, the V2 of jets in small systems like P gold. And then also interesting if you're looking at P gold to look at sort of an intermediate system. So looking at something like oxygen, where you could take some data and have something that's sort of in between, intermediate between the P gold and the gold. And then the last thing I wanted to show was sPHENIX beyond 2035. Since I know there's people in the room who are interested in the EIC and EPIC, I wanted to point out that the sPHENIX outer HCal, this detector right here, is actually planned to be the barrel HCal in the EPIC detector. And so at GSU, we're doing a lot of work in terms of tiles, understanding aging behaviors, that type of stuff, for the HCal tiles, because we're going to be using them for many years to come in the future EPIC detector. So that brings me to the end of the talk. So the conclusions basically are sPHENIX is really poised to make significant contributions to understanding of jet physics and QGP probes and jets. And in run 24, we completed really a lot of our goals. So we completed the commissioning for the detector in both LP and both gold. That means that we're really ready to take our high statistics data next year. We also collected a large PP reference data set with the calorimeter systems definitely, the tracking systems also, and to some extent with both combined. And so we will be able to do measurements with all of the systems and all of sPHENIX. And the last thing is we're really looking forward to future running in 2025 and potentially beyond.
Yep. It was a great talk, and I'm excited to do lots of quark matter. Can you go to slide 39? Mentioned there's some problems with the centrality classifications. I had a question first, just what you're using for centrality. Is it like the SCPD or is
it's the MBD?
MBD? Okay.
Yeah, the SCPD was not fully instrumented in right away.
Okay. So what was the problem you had?
I think there was just some issues in the actual calculation of the centrality bins. And basically no one's had time to go back and redo those because we're really focused on them.
Okay, so it's not like there's no detector problem.
It's not a detector problem, no, it's a.
Okay.
So I guess you said that the main issue with the tracking system is with the TPC, and I assume to measure heavy flavor, you would mostly make use of NBTX.
Yeah, so there definitely are studies ongoing about what we can get out of just the silicon tracks. Problem is that the silicon tracks really don't have good momentum resolution because they're so close together, you can't really get any bend in there. And so there's a possibility that we can use that data to do some tracking, but it's still sort of under investigation.
So then, maybe this is like obviously wrong, but can you measure the heavy flavor decay electrons with calorimeter?
You could, yeah, you mean you can measure electrons with the calorimeter. The problem is if you're trying to match a track to that, it's very difficult to project from the silicon where you don't really have a good handle on the direction all the way to the calorimeter.
Oh, okay.
Yeah.
So that's why having TPC tracks to match to calorimeter would be better.
Yeah.
Okay.
I have a quick follow-up question to that. So when you say calorimeter only, does that doesn't include the silicon or does?
When I say calorimeter only, I really mean calorimeter only. So the data set, a lot of it had the silicon in it also. And there are definitely people who are interested in looking at silicon plus calorimeter measurements, myself included. But it's unclear to us at this point if we will definitely be able to do something with that. And also the data, the plots of the luminosity that I showed are focused only on the calorimeter. So not every single one of those runs have the silicon in because they were also still commissioning during that time. But they're in a lot of it.
So maybe I have a question, but it will be difficult for you to answer. Because really, just we know this after TPC really came to reasonable conditions. One of the main problems background. And for example, during my shift, it stopped. It was nightmare. One bunch, and so on. So
Yeah.
Finally, it was found the reason for background or not. What is your understanding?
There is an idea of where the background is coming from. And we think that we should be able to, with a combination of some additional steering from the RHIC side and also some updates. So the background for the gold run is from in the MBTX. And so basically what happens is that particles hit the MBTX and it overwhelms the readout and then it can't read out anymore. And so we basically lose like half the MBTX in most of the data. And so with a combination of some reduction in the backgrounds, which we did have a lot of good studies giving the run at the end of this run, to understand where those backgrounds are coming from, and then also some updates in the firmware for the MBTX to really try and recover faster from these types of events.
I must be, because during the run I had a chance, to contact with my friends, including sPHENIX, of course. I have a lot of friends. So really I realized that really background the function from what direction particles are coming.
Yeah.
So this maybe not the gas.
Yeah, it's
But really after this location, sorry, I just finished my location, more or less found that very close to one, I would say, flange somewhere.
Yeah.
I did a super stupid proposal, maybe something inside of deep pipe with this condition. During connection, forget something. It will be interesting to check.
Yeah, the sPHENIX beam pipe is also very slightly tilted, which we don't think is a problem, but could potentially be contributing to the background as well. So
Which way?
Like it.
Oh, okay. I'm just trying to visualize. You're at it.
I think we should be able to get to the point where reduce.
I was wondering. Sorry, but that's. I found it.
Isaac, I have a question.
The general question about looking forward to 2025. And since we have you in the room coming and representing sPHENIX, I know like PU's requests are being drafted and are being submitted. So what can you tell us about from the sPHENIX side, how likely it will be that we actually push for different species of beams being done kind of in the isobar fashion that we did where, I mean, because there's chance about doing like, you know, rare earth metals in that alternating fashion, or even doing like a mimicking lead rod. So from sPHENIX, is there any actual chat about this? Or
So
is it
that
just-
the sPHENIX request really is, we need to get the gold data set. That is #1 priority. We have some issues, as I described in the PP data set, and so we probably will ask if there's time after the gold to potentially get more PP. And then I think after that, we're really interested in the small systems, so the people and the oxygen.
Okay.
It looks like, John, do you have a question you wanted to ask?
Yeah, first of all, Virginia, thanks for coming and nice talk. Good to hear results coming out of sPHENIX. Maybe an aside, Yuchi, it's good. Welcome back to you. I heard your voice. You asked a question. So on slide 58, I'm sure you're anticipating any questions or discussions on this. I just wanted to, I mean, the vast difference between the Atlas measurement and ALICE measurement in the end has to be attributed to something. And of course, sPHENIX will settle this. But maybe you could tell us what the differences are in the two different measurements, the techniques that are used, and even speculate why they might be so dramatically different?
That is a great question. I don't know that I can necessarily speculate what's different. I know, so I mean, there's some obvious differences just looking at the plot, right? The radius is slightly different. The atlas resulted in some RCP rather than an RAA. In terms of the techniques, the Elise result going down to very low PT was using a machine learning technique for the backgrounds. The background subtraction is a little bit different. If I really had to speculate, I would guess it's something in the difference of the background subtractions, but I really don't know.
Yeah, I would
To
guess
get-
that first in terms of always backgrounds or issues, question, how you deal with it. And I guess the other question is whether RCP makes a difference here versus RAA or not. I don't know. I don't expect an answer, but that's something I would wonder about.
Yeah, definitely.
Okay, thank you.
Perfect.
So, I mean, I understand like TPC is not designed really for PID for spinning, but do you know if they studied on like how the results look like or?
There's been some looks at like DDX. It kind of works, but not really, I would say.
I mean, it's not designed for it.
Yeah, it's not designed for it. You can do maybe some PID, but probably not
Okay.
anything very good. Yeah.
So, I think in the section where you talk about 2023 results, there's a plot of min bias versus outer HCal 2D plot.
Mhm.
Yeah, this one. So why is there some off diagonal points like along the y-axis?
So this is, I would say, very raw data first and foremost. We have had some instances where we basically drop like an event or two, and then sometimes the events can get misaligned. I think this one had the fix already in it, so I don't think it's that. But I think there might just be some like hot channel in the MVP or the HCal. Or something like that, but it's really not been cleaned up yet at this stage, because this was like mid day 4 of the first run.
Guess we're on the same wavelength.
Somebody
There's also
from-
the about this plot.
From your community told me that really it's going to be connected, not all charge particle reconstructed. Like moving,
Yeah,
practically this point should be moved on the right somehow. It's maybe not completely reconstructed, all charge particles.
yeah, there were also some changes early on in
Okay,
the
maybe remind me.
yeah, there were some changes early on in the NVD settings as well, so it might be that it wasn't at the optimal setting yet.
This normal working TPC will be improved.
While we're here, I was gonna ask, actually, you mentioned on this slide that this kind of agreement wasn't guaranteed because of the structure of the readout. Can you talk a bit about that?
Yeah, so every single system is read out individually. In fact, the EMCal is read out separately in 8 separate parts. And so we take all of that data and we just take it, and then we have to offline we combine the events. And so if you have things like dropping events every once in a while, stuff like that, that was a lot of the commissioning that was done in 2023 and between the runs, was really to understand all of the event combining. And the streaming event combining is its own problem beyond that, because that's even more complicated because you don't even have a trigger.
Right.
And so that's something that's being worked on now.
So when you do have a trigger, I'm not sure I understand what causes the event dropping.
It has to do with basically you're just taking too much data and it can just get overwhelmed.
Oh, I see. Okay.
Maybe I have one more question, Isaac. Virginia, in the run that just finished, with free streaming, does sPHENIX feel it was sufficient running to get open heavy flavor EP data?
Yeah, so we didn't quite meet the goal, but I think that the understanding, looking at projections is that we should be able to get the open heavy flavor measurements still. What's really gonna struggle is the things that require both the tracking and calorimeters, so things like the epsilon measurements. But yeah, the open heavy flavor, I think we should be able to have the measurements with the data set.
Okay, thanks.
Sorry, can I follow up on that
Yes.
again? So I guess if you don't have matching between MBTX and calorimeter, but can you just, since you have so much calorimeter data, but just forget about the information you have from MBTX and just construct the invariant mass peaks from calorimeter alone, is that possible for like quark-gluon measurements?
Don't think so. I'm definitely not a quark-gluon expert. Yeah, but I don't think that's possible.
Okay.
I think you really need the very precise momentum resolution for the quark-gluon, especially the separation of the states, and that's going to come from the tracking. The momentum or the energy measurement in the calorimeter isn't, nearly as precise as the momentum measurement that you can get out of the tracking.
But perhaps that's something Star can do.
That is something STAR can do or should do. But also Virginia was right in that you need the tracking to get the mass resolution if you want to really look at the quark-gluon.
It's something that STAR has done to its best of its abilities, but sPHENIX should be able to do it better because of the precision of the calories, the secondary agent and the micro vertex. We can't do much better with the statistics. But only measurement.
For run 23 through 25, the high luminosity runs, will that?
It's slightly high, but it's not really statistics. I mean, maybe you get to the 3S, but its resolution, can you resolve that as, let's say, like, can you resolve the 3 states and so on? That is the momentum resolution, not statistics always help, of course.
Yeah.
That to a large extent, maybe for the epsilon 3S, which we have an upper limit for, more data, but it would take a lot more because it's a huge amount of data that's being collected, but it's still maybe order of magnitude potentially more for STAR. That doesn't get you to without having a great resolution to where it's